All right, guys, so today we're talking about transcendental differentiation, which really boils down to doing differentials with log functions and e functions. So what we have here are a lot of the natural logarithmic properties that you probably haven't seen for a little while. You did all of this in Math 3, but it's maybe been a little bit. So just this first part's just a quick reminder. I'm not going to spend too much time, but basically what we're looking at, a log function, the basic graph of that, right here we have an asymptote. And the way that this function looks is we kind of just, what color do we want to do this in so that you can see it? We kind of get really close to 0 here, and then we just curve out to the right, okay? So we never actually hit 0, and that's why the domain, there's a parenthesis at 0, because we're never going to hit that asymptote. We're never going to hit 0, but it goes to the right infinitely. The range, it goes down forever, it goes up forever. It just takes a really long time to go up forever. It's continuous. I can draw this graph without picking up my pencil. It's increasing because when I go from left to right, it's going up, not down. And it's 1-to-1, meaning I can find the inverse of it because my x and y's have 1-to-1. It's also concave downward, which we haven't really talked about yet. All that does is kind of tell you the shape of the function. Like a parabola is concave up because it's a parabola. That's where the dip is. This one is, if you did the negative parabolas, if you flipped them over, those are concave down because that's the way they're concaved. So a few of the properties that you need to memorize and have down and good at says that the natural logarithm of 1 is equal to 0. And that kind of carries over because the log of, it doesn't matter what the base is, the log of anything to the 1 is equal to 0. Okay? So the natural log of 1 is the same thing as 0. If I'm taking the natural log of a times b, that's the same as the natural log of a plus the natural log of b. The natural log of a raised to the n, I can take this n and I can move it out in front, and it's n times ln of a. And then the natural log of a over b is equal to natural log of a minus the natural log of whatever's on the bottom. All right? Now be careful. If I have an a plus b inside, I cannot simplify that. If this was a multiplication, great. But if it's a plus, I can't simplify and just change that to the natural log of a plus the natural log of b. Okay, so a few quick examples of algebra that we haven't seen in a while. If it wants me to expand this logarithm, so basically this entire thing is inside my natural log. So the first thing I notice is I can take everything on top, the natural log of everything on top, and minus the natural log of everything on the bottom. So the stuff on the top is going to have a positive in front of the natural log. The stuff on the bottom is going to have a negative in front of the natural log. So starting with the top, I'm just going to rewrite this as the natural log of x cubed minus 2 raised to the 4th power. And then I get to minus the bottom, minus the natural log of x times the 5th root of x squared plus 1. And all of that is in my natural log. So we can separate this out a little bit. This 4 can come on down. So I could get 4 natural log of x cubed minus 2. Unfortunately, I can't split this up at all because of that minus sign. And then I get minus, but this one I can actually split because I've got x multiplied by this part. So this becomes minus the natural log of x minus the natural log of my 5th root of x squared plus 1. Now, if you remember our root trick, I can actually rewrite this one as negative natural log of x squared plus 1. I can move that 5 up here to be 1/5, which is nice with natural logs because now I can move that 5th to the front. So my final answer is 4 natural log of x cubed minus 2 minus the natural log of x minus 1/5 natural log of x squared plus 1. Now, the reason that we want to do this, I know that this looks bigger than the fraction, is when I'm doing the derivative, a lot of times it's so much easier to use this form than it is to try and do a derivative within a quotient, within a product rule, within a couple chain rules inside my ln function, okay? So this bottom one over here, remember, the stuff on the top is going to get a plus. The stuff on the bottom is going to get a minus. So technically, we start with the natural log of 2 times x cubed minus the natural log of 5yz. But remember our multiplication rules. I can take all of these. I can take the natural log of 2 and add the natural log of x to the third power. And right here, because it's minus this entire log, remember, if it comes from the bottom, it gets a negative. So minus the natural log of 5, minus the natural log of y, minus the natural log of z. Okay, and there's one more place we can simplify, and that's this 3 right here. All right, so if I simplify that one, I end up with natural log of 2 plus 3 natural log x minus natural log 5 minus natural log y minus natural log z. And that right there is going to be so easy to differentiate here in a minute when we're ready to do that. This last one, we're going backwards. We're going to condense it from this form and try to make it look like this one up here. We're going to try and go backwards a little bit. So anything that's positive, remember, that goes on the top. Anything that's negative is going to go on the bottom. And really, they're all just being multiplied together because all I have is a minus and a plus and a minus right here. And technically, there's a plus out in front. So on top, I'm going to end up with log 3x plus, where's my other positive? Here's my other positive, plus 2 log base 3 of z. Now, it doesn't matter what my base is. As long as all my bases are the same, they can all go together. And then on the bottom, I've got my minuses. So the 4 log base 3 of y, and this one right here, 6 log 3 of w. So I'm going to just condense those a little bit more. I'm going to put them all into one function. So this 2 right here goes up with my z. This 6 goes up with my w. And this 4 goes up with my y. So on top, I'm just left, I've got a big log base 3 of this big fraction. The x is going to go on top, and the z to the second power is going to go on top. And on the bottom, I'm going to have a y to the 4th, and I'm going to have a w to the 6th power on the bottom. Okay. So that's how we go backwards, which we're not going to do a lot, but it's been a while. So just remember how to do those things. Now, getting into the calculus, the derivative of natural logarithms and logarithm in general is awesome because the natural log of x is just 1 over x. The derivative of the natural log of x is 1 over x. If I don't just have an x in there, if I have a function like 3x squared or 5 divided by x, I have 2 different forms of the derivative. The derivative is just the derivative of what's ever inside your natural log on top and just the inside on the bottom. Or sometimes it's easier if you write it as 1 over the inside times by the derivative of the inside. So both of these mean the same thing, just sometimes one looks better than the other. And then the derivative of the natural log of absolute value of u is exactly the same as if it was regular u. You don't have to worry about that absolute value. Don't do extra stuff just because you see an absolute value sign there. Okay? So d dx, take the derivative of ln of 3x squared. So first of all, there's my u, that 3x squared, that's just what's on the inside. So if I'm using this form right here, I'm going to write 1 over, if I'm taking the derivative of a logarithm, I'm going to put a fraction bar. First thing I'm going to do. So 1 goes on top and u goes on the bottom. So just the inside, the 3x squared goes on the bottom. And then that's multiplied by the derivative of u. So I've got to put u prime, so the derivative of the inside, and that's just 6x is my derivative of the inside. Now this one I can rewrite nicely as 6x over 3x squared because things cancel. The x cancels on the top, and I'm just left with 1x on the bottom, and 6 over 3 cancels, and I'm just left with 2 on top. So my derivative is 2 over x. Okay. Again, here's our u. And let's go ahead and let's use this notation as much as we can. Let's just put the derivative of my dy dx is going to equal a fraction. And on top goes the derivative of the inside. So 4x. On the bottom just goes the original function, 2x squared. And when I cancel this x and the 2 and the 4 and the 2, I end up with 2 over x. So the derivative of these two functions is actually the exact same. Okay. The derivative of negative 2x times the ln of x, the natural log. So here we've got our product rule that we got to worry about. So product rule tells me here's one of my functions, here's my other function. Okay. So the derivative of the first, which is this one here, this we'll call our second. The derivative of the first, or if you're my f prime g plus g prime f'ers, I should be careful how I say that, huh? The derivative of the first, negative 2x, is just negative 2. The derivative of, or not the derivative of, we just keep ln of x the way that it is. And then we're going to add the derivative of the second, or g prime. So the derivative of ln of x is just 1 over x. And we have to multiply that by negative 2x. We just multiply that by the first. Okay, so when I simplify, this just becomes negative 2 natural log of x. And then this negative 2x we can move over, and that just becomes minus 2x over x. And those cancel. So really, I just get negative 2 natural log x minus 2. I'm okay with that answer. That looks good. Derivative of ln of 2x cubed. Now be careful. I can't just move this 3 to the front of the natural log because it's on the outside of these parentheses. It's not inside the natural log. So I'm going to have to use the chain rule on this one. So the chain rule tells me that I need to take the derivative of the outside, so 3, and then I leave the inside the same, and then the 3 comes down to be a squared. We go down by 1, and then I have to multiply by the derivative of the inside. So I need to find the derivative of the natural log of 2x. So be careful. It's going to be a fraction. On the bottom is going to be the 2x, just the normal inside the natural log. On the top is going to be the derivative of 2x, which is just 2. And those are going to go ahead and cancel out. So all I'm left with is 3 natural log of 2x squared all over x is what's left over on the bottom. And again, that's a great answer. That looks good to me. Okay, more examples. Let's take the natural log of a square root, because why not? First of all, we don't like square roots, so let's change that. Let's change this to the natural log of 3x minus 1 raised to the half, which works out great because with my natural log rules, I can take that 1/2 and move it to the front. So that actually becomes 1/2 the natural log of 3x minus 1. Now I don't even have to worry about that exponent. So when I take the derivative, f prime of x, my derivative is going to equal, we're using this over here. So I've got that 1/2 out in front. Remember the constant rule, or the coefficient rule there. The 1/2 is in front. Now I need to take the derivative of natural log 3x minus 1. So I'm going to make a fraction, and the 3x minus 1 goes on the bottom, and on the top goes the derivative of the 3x minus 1, which is just 3. So when I combine all this together, I end up with 3 on top. And what do I get on the bottom? 6x minus 2. That looks good to me. I'd be okay with that answer. Okay, this looks a little messier. It's about time. Those have been pretty quick going forward. So this is an example of one that you would want to expand. We want to use those log rules to expand this out and make it a little bit more easy to work with. So remember, the things on top are going to be pluses. The things on the bottom are going to get minuses. So on top, I have the 2x multiplied by the x squared plus 3 squared. So that means that I get the natural log of 2x plus the natural log of x squared plus 3 squared. I'm going to be able to move that 2 down here in a minute. And then everything on the bottom, I'm going to minus. I'm going to minus the natural log of the bottom, the natural log of 3 root 2x cubed, oh my, plus 1. So let's do some rewriting here. Natural log of 2x. This 2 can come down in front. 2 natural log of x squared plus 3 minus this piece right here. I can rewrite that as the natural log of 2x cubed plus 1 raised to the 1/3 and get rid of that radical, which is nice because then I can just bring that 1/3 down in front. So I'm going to put minus 1/3 natural log of 2x cubed plus 1. So I know that doesn't look a lot better, but it's going to be a lot easier to do the derivative of this. So if I'm going to take the derivative now, let's take f prime of x. It's going to equal, when I do the derivative of the natural log of 2x, I'm going to get a fraction. 2x is going to go on the bottom, and on top goes the derivative of 2x, which is just 2. And then 2 natural, I guess we could have split that up. I'm looking at that thinking that could have just been natural log of 2 plus the natural log of x, but we're going to end up with the same answer because the natural log of 2 just goes to 0. Really quick, natural log of 2. If I had split these up to be natural log of 2 plus natural log of x, the natural log of 2 becomes, the 2 stays on the bottom, the derivative of the 2 goes on top, and that's 0. So the natural log of a constant is just 0. So I'm just left with natural log of x, which is what's going to happen because these 2's are going to cancel out and it's going to turn into 1 over x. So no big deal. Now I need to take the derivative of 2 ln x squared plus 3. So I've got that 2 in front, and then I have a fraction. Whatever's inside goes on the bottom. And then on top goes the derivative of the inside. So 2x would be my derivative of the inside. Okay. And then I need to take the derivative of this one. So I still have the 1/3. The derivative of the natural log, again, I'm going to do a fraction. On the bottom, I'm going to put the function 2x cubed plus 1. On the top, I'm going to take the derivative of that, which is 6x squared. So a little bit of rewriting. 2 over 2x just becomes 1 over x. 2 times 2x becomes 4x over x squared plus 3. And negative 1 times 6x squared is just 6x squared. And on the bottom, I end up with 6x cubed plus 3 Oh, maybe I shouldn't have multiplied that. I maybe should have just canceled some stuff out first. Because look, a 3 goes into all of these terms. So it rewrites as 1 over x plus 4x over x squared plus 3 minus, if I factor out a 3 of all of this, this is a 2, this was a 2, and this becomes a 1. So I end up with minus 2x squared over 2x cubed plus 1. And I think that's okay. I think there's no way we're going to get common denominators with a reasonable amount of work. So we're going to go ahead and leave those the way that they are. Okay, that would be your derivative. All right, so using absolute value. I see so many people do this one wrong because they think they have to include the absolute value. It doesn't matter. It's as if it wasn't even there. Okay, so when it says find the derivative of the natural log of sine of x, I'm going to ignore that absolute value on the outside of it. It's not going to change my answer. So my f prime of x is just going to equal a fraction. On the bottom is going to go sine of x. On the top is going to be the derivative of sine of x, which is cosine of x. Well, that's kind of cool because cosine of x over sine of x, that's actually cotangent of x. So that would be your derivative, cotangent x. Okay. This one on the right, x to the x. Again, one that I see people try to like use the power rule. They try to take this x and bring it down and they say, okay, the derivative is x times x to the x minus 1. No, no, no. Everything about that doesn't work. So please don't do that. It's not going to work that way. Okay. What we actually want to do is, and again, we haven't done this for a while. This is stuff that you did clear back in secondary math 3, but remember f of x is kind of the same as saying y equals x to the x. And my issue is that I have an x raised to another x, so I can't use my exponent rule there. So what I'm going to do is I'm going to actually take the natural log of the left, and I'm going to take the natural log of the right. And the reason I want to do that is because I can move, now that I have the natural log of x to the x, I can move my x to the front. So this becomes natural log of y equals x natural log of x. Now I'm going to go ahead and differentiate. So the derivative of the natural log of y is just 1 over y, but I can't forget my dy dx because we're taking the derivative in terms of x. So I need that dy dx, but otherwise it's the same as the natural log of x. And that's going to equal x times, well, I guess we better use the product rule, huh? Because that's not a constant, that's an x. So here we've got the product rule that we need to use. So it tells me that the derivative of x, that's just 1, times the second term, natural log of x, plus the derivative of the natural log of x, well, that's just 1 over x, times by our first function there, which is x. So I end up with 1 over y dy dx equal to natural log of x plus this just becomes x over x. So that just becomes 1. Natural log of 1. That's kind of nice. So dealing with that 1 over y, because I don't want 1 over y. I want just the derivative dy dx. So I need to get rid of 1 over y. So what I'm going to do is I'm going to times both sides by y. So over here, those cancel, and I'm left with dy dx is equal to, do we want to, yeah, let's go ahead and distribute that y. So we end up with y natural log of x plus y. Okay. Now, in this one, we could clean it up a little bit because if I can avoid it, I don't want y to be in my formula. And if I go clear back up here, I've got y is equal to x to the x power. So I can go ahead and plug that in wherever I have a y. So instead of y ln x, I'm going to put x to the x, natural log of x. Oh my gosh, that's a mouthful. Plus x to the x. That's a lot of x's. But that's my derivative, okay? Not too bad. I know it looks a little bit messy there for a minute, but that's kind of the method that I would use to do that one. Now we're taking the derivative of e to the x, which requires us to kind of remember an old rule. So again, I'm going to change this to y equals e to the x, but this is a really cool derivative because if I do what we did before on this other problem and I take the natural log of y equals the natural log of e raised to the x, well, that says the natural log of y is equal to x times the natural log of e. Now, if you remember much about logarithm properties, the natural log of e is equal to 1. So this just becomes the natural log of y equals x times 1, which just means the natural log of y equals x. So now when I take the derivative of both sides, the derivative of natural log of y is 1 over y times dy dx. Don't forget the dy dx, which equals the derivative of x. Well, that's just 1. And now, like before, to get rid of 1 over y, I'm going to times by y on both sides. So dy dx is equal to y. And here's where this is really cool. Y is equal to e to the x. So if I plug that in, the derivative is just e to the x. So the derivative of e to the x is itself. It's just e to the x. Let's hope that one comes up on the AP test for you. It's its own derivative. That would be nice, right? Okay, so let's try that. Well, a couple of things that you maybe haven't seen in a while. We just did this one right here. The natural log of e to the x is x because the natural log of e just goes away. And e to the natural log of x is also just x. Okay, those are big ones. So if f of x is equal to the natural log of x and the inverse of x is equal to e to the x, then this is also true. Y is equal to e to the x if and only if x is equal to the natural log of y. So we're not going to get into this one too much. We'll talk about that maybe a little bit more later. We're mostly focused on what we have up here, okay? So if I've got 10 equals e to the x plus 2, simple way to get rid of that exponent up there is change this to the natural log of 10 equals the natural log of e to the x plus 2. Because this goes away, and I end up with natural log of 10 just equals x plus 2. So I'm going to minus 2 from both sides. And be really careful, this is not natural log of 10 minus 2. This is the natural log of 10 minus 2. And that's going to equal x, okay? So it just wanted me to solve for x. I didn't have to do any differentiation there. It just wanted x by itself. So this side here, ln of 6x minus 2 equals 5. Well, I'm just going to raise both sides to the e. So ln of 6x minus 2. And this is equal to e to the 5. Well, that just means 6x minus 2 is equal to e to the 5. So I can add 2 to both sides. So 6x equals e to the 5th plus 2. So when I divide by 6, x equals e to the 5th plus 2 divided by 6. Okay? Again, all old stuff that you've done in the past. We just haven't really seen it in calculus yet. Okay? So a couple reminders about log or e functions, our exponential functions here. If I have e to the a times e to the b, that's just e to the a plus b. And e to the a divided by e to the b is e to the a minus b. If you're looking at what the function looks like, if this is my general function, I've got an asymptote right here at y equals 0. And my function kind of goes like this. It follows this asymptote and then it shoots up. Okay, so my domain is negative infinity because it goes to the left forever and it goes to the right forever. My range, it never hits 0 because of that asymptote, but it does go up forever. It's continuous, it's increasing, it's 1 to 1, and it's concave up. See how from left to right, it's up facing. And then the limit as I approach infinity to the left, my limit goes to 0. I'm getting closer and closer to 0. As I go to the right, I'm getting closer and closer to infinity, which means that it's undefined. It doesn't exist up there, okay? All right, so putting this into calculus, we'll do a couple of these really quick. Your video's running long again. The derivative of e to the x is just e to the x. We already did that one, right? The derivative of e to the u is e to the u, but then you have to multiply by the derivative of u. Okay, it's e to the u multiplied by the derivative of u. So down here, the derivative of e to the 3x squared plus 1 is e to the 3x squared plus 1, but I have to multiply by the derivative of my exponent. So that's just going to be, the derivative is going to be 6x. And so I would rewrite that as 6x e to the 3x squared plus 1. Okay, and that's it for that one. The one on the right, e to the negative 2 over x. The derivative of e to the negative 2 over x just becomes e to the negative 2 over x. But then I have to multiply by the derivative of the exponent, which is really, that's just negative 2 times x to the negative 1. If I make this x to the negative 1, or x to the 1 and move it up, it becomes x to the negative 1. So when I take the derivative of this, I get negative 1 times negative 2. That's positive 2. And then I get x to the negative second power. Okay, which just becomes what? This x to the second power goes to the bottom. So I get e negative 2 to the x. And my 2 is going to stay on top. And my x squared is going to go ahead and move to the bottom and become a positive. Okay, so that just becomes 2e to the negative 2 over x times x squared, or divided by x squared.